Welcome to AWS Mastery Labs, turning AWS chaos into clarity with bite-sized tutorials, hands-on labs, and exam-smashing tips. In this video, we will explore how encryption works in Amazon S3 and why it's essential for securing your data in the cloud. We'll break down the different types of encryption supported by S3, including server-side and client-side encryption, and explain how each option works, the use cases they're best suited for, and the trade-offs involved. Let's get started. Amazon S3, Simple Storage Service, is a foundational service in the AWS ecosystem, designed to offer secure, durable, and highly scalable object storage for a virtually unlimited range of use cases. Often described as infinitely scaling storage, S3 can seamlessly accommodate the needs of a single developer or the most data-intensive enterprise workloads, without the need to manage infrastructure or worry about capacity planning. One of the standout features of Amazon S3 is its simplicity. It provides a straightforward web services interface, available through the AWS Management Console, SDKs, CLI, and REST APIs, that allows users to store and retrieve any amount of data from anywhere on the web. It also integrates effortlessly with a vast array of third-party tools and AWS services, enabling developers to build complex workflows and scalable systems quickly. S3 is known for its exceptional durability, with AWS guaranteeing 99.9999999%, 11 nines durability for objects by redundantly storing data across multiple facilities. This makes it an ideal choice for backup and restore solutions, data archiving, and disaster recovery scenarios. S3 also supports a broad set of features like lifecycle management, replication, encryption, and access control, giving users fine-grained control over how their data is stored, accessed, and managed. Because of its reliability, scalability, and performance, many modern web and mobile applications use S3 as their content backbone. It's especially popular for serving static assets like HTML, CSS, JavaScript, images, and videos, often in combination with services like Amazon CloudFront for global content delivery. Businesses leverage S3 to build data lakes, support analytics workflows, host static websites, manage logs, and much more, making it not just a storage service, but a key enabler of innovation across industries. Securing data in transit is a foundational aspect of protecting sensitive information stored in Amazon S3. All data exchanged between clients and S3 can and should be encrypted using industry-standard protocols to prevent interception and tampering during transmission. Amazon S3 supports SSL/TLS (HTTPS) for secure data transfer. This ensures that every interaction with your S3 buckets, whether uploading, downloading, or listing objects, is encrypted end-to-end. Enabling HTTPS is as simple as using the appropriate endpoint, but for tighter control, you can enforce it explicitly. Bucket policies can be configured to deny any request made over an unencrypted connection, ensuring that all access is done securely over HTTPS only. When using tools such as AWS SDKs or the AWS CLI, they default to TLS 1.2 or higher, providing strong encryption and keeping your data transmission secure by default, without requiring additional configuration. In environments where mutual authentication is required, Mutual TLS, MTLS, offers an enhanced level of security by requiring both the client and server to present valid certificates before a connection is established. While Amazon S3 does not natively support MTLS, you can implement it indirectly using other AWS services such as Amazon API Gateway, AWS Network Load Balancer, NLB, and AWS Private Link. This approach is particularly useful for regulated industries or internal systems that demand strict identity verification at both ends of the communication. By securing data in transit using these capabilities and extending protections through additional AWS services when needed, you can build a highly secure and resilient architecture around your S3 usage. Securing data at rest is a critical component of any data protection strategy, and Amazon S3 makes it seamless with built-in encryption capabilities. Amazon S3 supports server-side encryption, SSE, which means that all data is automatically encrypted as it is written to disk and decrypted when accessed, with no changes required from the user. This ensures that your data remains protected even if the underlying storage hardware is compromised. Encryption is performed using Advanced Encryption Standard, AES, 256-bit symmetric keys. a widely adopted and highly secure method recognized by the industry for its robustness and reliability. You can enforce encryption through bucket policies and by setting default encryption on a bucket. This ensures that every object uploaded to S3, whether by users, applications, or services, is encrypted automatically, helping maintain compliance and reduce the risk of misconfigurations. For scenarios that require tighter control over encryption keys and processes, especially in regulated environments, you can opt for client-side encryption, where data is encrypted before it leaves your application. This ensures that AWS never has access to the unencrypted data, giving you full responsibility and control over encryption and key management. Server-side encryption with S3 managed keys, SSE-S3, offers a simple yet powerful way to protect your data at rest without adding complexity to your operations. With SSE-S3, Amazon S3 automatically encrypts each object using AES 256, a strong symmetric encryption algorithm, before storing it on disk, and decrypts it transparently whenever the object is retrieved. This means that from a user's perspective, encryption is entirely seamless. There's no need to modify applications or workflows to benefit from it. One of the key advantages of SSE-S3 is that encryption keys are fully managed by AWS. You don't need to create, rotate, or maintain keys yourself. AWS handles everything behind the scenes. This makes it an ideal solution for organizations that require encryption but don't want to deal with the operational overhead of managing encryption keys. There are no additional costs associated with SSE-S3 beyond the standard S3 storage and request pricing, making it a cost-effective way to meet encryption requirements. You can enforce the use of SSE-S3 through S3 default encryption settings or bucket policies, ensuring that all data uploaded to your buckets is automatically encrypted, whether by your team, external users, or integrated AWS services. SSE-S3 is best suited for environments where compliance or internal policy mandates encryption, but key management responsibilities are not required to be handled by the customer. It offers strong security with minimal setup, making it a go-to option for many secure cloud workloads. As illustrated, the appropriate HTTPS header must include the key set to AES 256 to activate this feature. This header instructs Amazon S3 to automatically encrypt the object using SSE-S3 as soon as it is uploaded to the bucket. SSE-S3 is best suited for environments where compliance or internal policy mandates encryption, but key management responsibilities are not required to be handled by the customer. It offers strong security with minimal setup, making it a go-to option for many secure cloud workloads. Amazon S3 supports SSE-KMS, a powerful encryption option that leverages the AWS Key Management Service to provide enhanced security and greater control over encryption keys. With SSE-KMS, each object is encrypted using a unique data key, which is itself protected by a KMS Managed Customer Key, CMK. There are two types of encryption keys available when using SSE-KMS: AWS Managed KMS keys and Customer Managed KMS keys, CMKs. AWS Managed KMS keys, also referred to as the default AWS/S3 keys, are automatically created and fully managed by AWS. They provide a simple, hands-off experience, ideal for users who want encryption without the overhead of key management. You don't need to create or rotate the keys, and AWS ensures they're securely stored and used. On the other hand, customer-managed CMKs offer much more control and customization. These keys are created, owned, and managed by the customer within the AWS Key Management Service. With CMKs, customers can define their own access controls using IAM policies and KMS key policies, specify who can use or manage the keys, enable automatic key rotation, and even create key aliases for easier reference. This level of flexibility is essential for organizations with strict compliance, auditing, or governance requirements. Choosing between these two options depends on the level of control and security your workload demands. AWS managed keys are ideal for convenience, while customer-managed CMKs are best for granular control and compliance. SSE-KMS integrates tightly with IAM and key policies, enabling fine-grained access control. It also provides detailed audit logs through AWS CloudTrail, helping you track how and when your keys are accessed for compliance and security visibility. For organizations that require stricter governance or need to meet regulatory requirements, SSE-KMS supports automatic key rotation for CMKs and allows you to enforce encryption via S3 bucket policies or default encryption settings. However, because it involves additional KMS API calls during both encryption and decryption, SSE-KMS introduces a slight increase in latency and cost. As illustrated, the appropriate HTTPS header must include the key set to AWS KMS to activate this feature. This header instructs Amazon S3 to automatically encrypt the object using SSE S3 as soon as it is uploaded to the bucket. Overall, SSE-KMS is ideal for workloads that demand strong data protection, comprehensive access control, and detailed auditability. While SSE-KMS offers enhanced security and greater control over encryption keys, it does come with a few limitations that should be considered, especially for high-performance or large-scale workloads. First, each encryption and decryption operation requires a direct call to AWS KMS, introducing additional latency compared to SSE S3. While often negligible for small workloads, this added processing time can impact performance in latency-sensitive applications or bulk transfers. Another important consideration is that AWS KMS enforces request rate limits. For high-volume applications, especially those uploading or accessing objects at scale, these limits can lead to throttling, which may cause delays or errors if not properly managed. There are also additional costs associated with using customer-managed KMS keys, CMKs. These include charges for API requests to KMS, key usage, and optional features like automatic key rotation. Over time, these costs can add up, especially in environments with frequent object access or encryption operations. Permission management becomes more complex with SSE-KMS. Unlike SSE S3, which is largely managed by AWS, SSE-KMS requires administrators to define both IAM policies and KMS key policies. This dual-layer approach, while powerful, adds complexity and increases the chances of misconfiguration if not carefully handled. Another limitation is that KMS keys are region-specific. This means if you're using cross-region replication for your S3 buckets, you'll need to create and manage a separate KMS key in each target region, adding to operational overhead. Finally, some features, like S3 transfer acceleration, are not compatible with SSE-KMS, limiting the scenarios where this encryption option can be used. While SSE-KMS is a robust choice for secure and compliant workloads, it introduces additional complexity, cost, and operational considerations that must be weighed carefully against the benefits. SSE-C, server-side encryption with customer-provided keys, offers a highly secure encryption model in Amazon S3 by allowing customers to retain full control over their encryption keys. With SSE-C, users supply their own encryption key for each S3 request, ensuring that AWS does not store, manage, or retain the key at any point. This model provides a strong security boundary. Since the encryption keys never persist within AWS infrastructure, the risk of key exposure is minimized. S3 uses the provided key only temporarily to perform the encryption when an object is uploaded and decryption when it is retrieved. Once the operation is complete, the key is discarded from memory. However, SSE-C demands robust key management on the customer's part. Organizations must implement their own secure storage, key rotation policies, and access control mechanisms. Any mismanagement or loss of these customer-provided keys could result in permanent data inaccessibility. A critical operational consideration with SSE-C is that the correct encryption key must be included in every request, whether uploading new data or retrieving existing objects. Without the matching key, S3 will deny access to the object. It's also important to note that SSE-C is not compatible with several S3 features, including S3 cross-region replication, AWS KMS integration, and S3 transfer acceleration. This limits its applicability in scenarios requiring advanced storage capabilities or high-speed global distribution. As illustrated, the encryption key must be included in the HTTPS request headers to enable SSE-C. This triggers automatic encryption of the object using the provided key as soon as it reaches the S3 bucket. SSE-C is best suited for highly regulated environments or use cases where organizations must retain absolute control over their encryption keys. However, it requires meticulous planning and secure key lifecycle management to be effective and reliable. Client-side encryption in Amazon S3 provides an added layer of data protection by ensuring that data is encrypted before it ever leaves the client's environment. This means the encryption process occurs locally, and the encrypted data is then uploaded to S3, keeping the raw, unencrypted content completely out of AWS infrastructure. Customers have the flexibility to manage keys in two ways. They can either use keys managed by AWS Key Management Service, KMS, or bring their own customer-managed keys. Regardless of the method, AWS never stores or has access to these keys, so users are fully responsible for securely storing and managing their encryption keys. Without the correct key, retrieving and decrypting the data will be impossible. This approach offers a strong security model, making it ideal for highly sensitive workloads where full control over data confidentiality is required. However, it also comes with additional complexity. Implementing client-side encryption typically requires the use of AWS SDKs, encryption libraries like the AWS Encryption SDK, or a custom-built encryption solution. In this process, the client is fully responsible for handling the encryption operations before interacting with S3. As illustrated, the client application takes the original file along with the encryption key, either generated locally or obtained from a key management system, and encrypts the file locally. The result is an encrypted object, which is then uploaded to the S3 bucket using standard put operations. Since Amazon S3 only receives and stores the encrypted version of the data, it plays no role in the encryption or decryption process. Later, when the object is retrieved, the client must again supply the same encryption key to decrypt the data locally. This ensures that only clients in possession of the correct key can access the original content, keeping the data completely protected, even if unauthorized access to the S3 bucket occurs. As organizations scale their cloud environments, ensuring that all data stored in Amazon S3 is encrypted becomes a critical security and compliance requirement. However, relying on application-level controls or user discipline alone to consistently apply encryption can lead to gaps in data protection. To address this, AWS provides built-in mechanisms for enforcing encryption at the bucket level. These approaches, such as default encryption and bucket policies, allow administrators to mandate encryption automatically, reducing human error and ensuring a uniform security posture. Default encryption provides a simple yet effective way to ensure that all objects uploaded to a specific S3 bucket are automatically encrypted without requiring users or applications to explicitly request encryption during upload. This setting is configured at the bucket level and enforces encryption on every new object stored in that bucket. When default encryption is enabled, Amazon S3 will apply encryption using the selected server-side encryption method, either SSE-S3, where AWS manages the encryption keys on your behalf, or SSE-KMS, which leverages AWS Key Management Service for more granular key control and auditability. This ensures compliance with internal and regulatory data protection policies without placing the burden of encryption logic on client-side applications. Because encryption is applied automatically, default encryption significantly reduces the risk of inadvertently storing unencrypted data. It's especially useful in environments with multiple users or automated systems where enforcing encryption manually at each interaction would be impractical or error-prone. Overall, default encryption offers a streamlined and reliable approach to enforce baseline encryption standards across your S3 storage. Bucket policies offer a powerful mechanism to enforce encryption requirements by giving administrators fine-grained control over how data is uploaded to S3 buckets. Unlike default encryption, which passively ensures encryption is applied to all new objects, bucket policies allow you to actively enforce compliance by denying any upload requests that do not meet specific encryption requirements. These policies can be configured to enforce server-side encryption using SSE-S3, SSE-KMS, or SSE-C, depending on your security needs and key management strategy. For example, you can write a policy that denies all put object requests unless the request explicitly specifies encryption using a particular method or key. Bucket policies are highly flexible and can incorporate conditional logic, allowing rules to be applied based on factors such as source IP, object tags, user identity, or encryption method. This makes them ideal for organizations that require strict compliance and want to ensure that only secure, encrypted uploads are accepted. Both default encryption and bucket policies play crucial roles in enforcing encryption standards within Amazon S3, but serve different purposes. Default encryption offers a simple, automated way to ensure all new objects are encrypted upon upload, requiring minimal configuration and supporting SSE S3 or SSE-KMS. It's ideal for enforcing organization-wide encryption defaults without needing changes from application developers. On the other hand, bucket policies provide a more granular and enforceable mechanism, allowing administrators to define precise conditions under which encryption must occur, effectively blocking unencrypted uploads and ensuring compliance with security mandates. When used together, these two features provide a robust, layered approach to securing data at rest in S3, balancing ease of use with strict enforcement where needed. Thank you for joining us in this video. If you haven't already, we'd love for you to subscribe to our channel to stay updated with our latest content. We look forward to sharing more insights with you in another video. Until then, keep exploring. And thank you for watching.